Okay, to start. Oh, more stuff. Oh, interesting. Okay, let's start. Sorry, a little bit delayed. Today, our goal is to finish up where we left off last time, talk a little bit more about ResNets. There's a couple of things I want to talk about, and I want to introduce the conv-next architecture to help you understand better, how these ideas have evolved since the original ResNet. Then I want to spend a little bit of time briefly. I'll use a subset of Sergey's slides to talk about vision in beyond the simple problems we've been talking about, just to show you give you a taste of how in practice you might have to modify the neural net architectures to solve other problems while maintaining the same spirit. And then we're going to start into graph neural nets, which are an interesting generalization of conv-nets and help you understand which ideas were very specific to images and which ideas generalize more broadly, so you can understand how things are built up. And GNNs are basically on the path to understanding the transform architecture, which is very important in lots of problems today. So just to hopefully discussion helped a lot with understanding a little bit what's going on with the residual connections. So basically one comment I wanted to make about them before I switch over to talk about conv-next. So this pen is kind of dying. Dead pen here. So recall, the key idea behind the ResNet architecture was instead of something that looks like this, we do that, okay? So here, G is some learnable function, and then you compose these into deeper layers, basic building block. We do this thing as our basic building block. And the idea was, by doing this, having this connection that skips over the function block and basically makes it that it's called the residual connection, right? So it basically says that instead of viewing the function that you're learning as something which transforms completely the input into the output, you view it as something that makes a modification to the input to get the output. And by doing this, when you stack this into many, many layers, there's always going to be a gradient, that signal that's coming back to all of these F blocks, because it can come through these connections, where it'll just effectively all the F blocks will be adding to the final thing. Okay? We talked about that last time. We introduced this idea. You saw a little bit more about this in discussion. And we also talked last time about how this feels like, if you think of this F as doing something small, this feels like a discretization of an ODE, right? We take a little time step. So F here represents, x dot equals f of x type of thing. Okay, so this is like a little bit change that's coming in. Okay, so that's we talked about that last time. Hopefully that's all very clear. So I wanted to talk a little bit more about brief comment on what should be inside this F block. Okay, so in particular, like an exercise for you to think about. Let's compare the following two things. X comes in, there's some convolution, there's some nonlinearity, ReLU, and that's it. Okay, suppose this is the candidate for the F. So it's like one classical conv layer, again, classical conv nets. Compare this to another choice. A conv layer ReLU and let's just say for purposes of thinking, a 1-by-1 linear layer. Just first in spirit, just compare these two. Okay, so these are both candidates for what you can put inside the F. Let's try to understand, how we're thinking about things a little bit, to understand why you might prefer one over the other. Okay, so if this is the thing that's inside your F, okay, like this is the architecture inside the F. So again, you should think about, sorry, I'm gonna there's also, to make it explicit, there's biases also that can come in. Okay, so different biases. So just think of it this way. What kind of functions F can you realize with this versus this? And then we can think about what more stuff you might want to do. Okay, anyone want to comment on this? It's like a little aside of like what's going on. Like, why do resonant blocks a little bit look the way they do? Yeah.
So this is kind of, I'm not sure if the analogy works, but more so as the document instead of just transforming it using comp.
Okay. So what do you mean? So can you repeat what you're saying? Sorry, I didn't quite catch.
Yeah, so I was thinking if it's more like augmenting the picture instead of just transforming it using convolution, because of adding the original signal back into the X.
Okay, so yeah, that's this. That's the comparison of this to this. You're right. That's how we think about ResNets, is they have this, the transformation they're doing is a delta or a change to the original, whatever their input is, as opposed to a transformation. That's correct for this to this. What I want you to do now is to think about different, so this is 4f. In the context of these f's, these increments, think about this versus this. Yeah. Okay, so the question is, are they the same set of expressible functions? So that's a tricky question, because I'm building up to something, but it's a kind of a tricky question. So if you just look at them in isolation, just by itself, this and this are actually a different set of expressible functions. Okay? So can anyone tell me a kind of function, if you want to just think about, one dimension or something, right? Make it really simple for yourself. Something that you can express here, but you cannot express here. Yeah, in the back.
Maybe something that depends on.
Something that depends on position. So, okay, when I wrote here a 1-by-1 linear layer, I mean everything is going to keep the convolutional architecture. Okay, so we're not going to allow things to have a dependence on the absolute position of where the convolution is happening. So when I said 1-by-1 linear layer, I mean that whatever you're doing as a convolution, so this, whenever a conv layer, right, has many channels that it's producing, right? However many channels are in the X, right? The same number of channels are being produced here. This can be a convolution that looks across all those channels. There's some biases that are added, and then it's ReLU'd. And then when I say 1-by-1 linear layer, I mean this is going to be something, you can think about it as, okay, so maybe I shouldn't write linear layer. I'll write it, I wrote first as linear layer, then I wrote convolution. So let's call it 1-by-1 conv layer. Right? And I want to point out it has a bias, which means this is also acting convolutionally. So but it's a 1-by-1, which means it only looks at each pixel separately. However, it looks across the different channels in that pixel. Okay? So that's what I meant. So yeah, thank you for catching that basic little ambiguity in what I wrote. I wanted to emphasize that there's no nonlinearity here, but yeah. Okay, so can anyone tell me, again, the question is, can anyone say what kind of function maybe this can express that you cannot express here? Yeah.
I think the one on the right can have negative outputs.
Yeah, so does everyone hear that? So the one on this side, this can have negative outputs, whereas this one cannot. So there's a clear difference in expressive capability of just these individual little blocks, okay, that you should just be aware of. So that's interesting, right? Because what's happening here is, if you just think of the extreme case of this convolution as being, again, a 1-by-1, it's typically not in a ResNet. ResNet usually these are 3-by-3s. But if it's a 1-by-1, then what you're really doing is you're taking a linear combination of the different channels in X, right? Computing a bunch of different, however many outputs there are here, a bunch of different such linear combinations for the different channels of this, making them all have a nonlinearity, and then you're doing a linear combination of them. So it's like a little MLP that's happening here, where you can basically approximate any piecewise linear function using this. But here, you kind of can't, because you don't have that final thing. So just if you think about this again from the perspective of, if you wanted this thing to have the expressive power of some differential equation, x dot equals f of x, you might want to be able to have negative f, right, in here. And so you can kind of see that already from the thinking, I didn't say this enough last time, already from the thinking of a ResNet, you already start changing your understanding of what the individual blocks should be that get stacked together. Instead of being a single kind of a very doctrinal kind of MLP oriented perspective where, a layer shall consist of, in terms of your mind, a set of linear weights followed by a nonlinearity followed by adding a bias, right? Or, linear weights, adding a bias, nonlinearity, that's it, right? And that's the MLP kind of doctrine of what a layer consists of, but here you can see that that's not really the right building block to think about. You need something more than that. Okay, so this is like a little comment on why ResNets actually have more stuff inside F before you have this residual connection kick in. Okay, any sort of questions on that? I know this is a point of confusion that I often get asked about, so I wanted to make sure I just talked about it. Okay, great. Now, you could ask the question, when you compose these things, right, then is there a difference between these two, right? The answer is yeah, there's still a little difference, right, even after the composition because of how the residual is coming in. Okay, so nowadays, we can reason about it this way, the way we thought about it. Actually, in the original historical development of these residual connections, people actually experimented differently, right? I believe what happened was people first experimented with just saying, okay, I have this, let me add a residual connection and see how it works. And it did okay. The gradient problem was solved, but it wasn't as great. Then they said, maybe I'll only have the residual connection after every 2 of these. And that worked much better. Because you can see, if you stack 2 of these together, you kind of get this kind of effect. If you get to do some combination of the outputs of the railroad. Okay? And so that's why sometimes people will call them skip connections that way. Because they skip over one thing. They're not directly over one layer. Okay? But we don't think of them that way. We think of it more as providing another path and thinking of this block as being something more interesting. This perspective turns out of kind of allowing ourselves for a richer compositional block is what generalizes nicely to other domains and other kinds of problems, including graph neural nets. Okay, yeah, question.
They put the skip connection, do they put it after the prelude of the second layer?
Yeah, so I'll draw a picture. I'll show you where they how they do it in actual and what the current best practice is. So I'll switch now to the some of these again slides that modifications of slides that Sergey used, but they're quite nice. In general, for the course, you should view the material that was run in spring 21 by Sergey Levin as being like those are nice slides. You can use them to complement what I'm doing in lecture. I will sometimes not go into as much detail at some parts, and I'll expand on other parts. But those are nice kind of reference for you. Let me. Okay. Work. Something is happening. Okay. Yes. Okay. Why this still takes so long these days is beyond me, but. Okay, so if you look at this, right, this is how the classic ResNet blocks are built. Okay, so ComNext was so there's like history. I'm telling you stuff out of order, but just so kind of conceptually, it's easier for you to learn this way. This is how a ResNet block was put together. So the classical ResNet block had, first it said, okay, I'm going to do, after much manipulation, right, of like where to put the skips, right, where to put the residual connections. So let's take a 256 channel thing in. Let's first do linear combinations of that, each pixel, linear combinations across the different channels for each pixel. That's what the 1 by 1 means. And 64 means let's create 64 channels out. So then, having 64 channels out that are linear combinations of the previous 256 channels, you then do a 3 by 3 convolution, and you do 64 of them to create 64 channels of output. So after this, though, they used to put a ReLU right there. They used to put, okay, let's also put a ReLU here. And then also let's do batch norm. Then here, let's do a ReLU and batch norm. And then let's go back to 256 dimensions. So let's do 1 by 1, means, again, linear combinations of those 64 things. But let's do it 256 times to return to the original size. And then let's do batch norm again. And then they would take the whole thing, add the residual, and then ReLU. Okay, that's the final design that they by iteration and experimentation, that they converge to. And so ConNext is an approach that was developed, relatively recently. A paper came out last year, in which they said, let's revisit what this looks like in light of the experiences we have in other domains. Kind of fresh rethink of how a ResNet architecture should be. In particular, this was very inspired by what the progress of something called vision transformers we'll talk about later. But at some level, that historical development doesn't matter for your understanding. You can understand this kind of on its own terms. So what it did was they said, okay, let's move this around a bit. So let's actually change the dimensions to 96. Again, that was experimentally chosen. And let's do a 7 by 7 convolution instead of a 3 by 3. So let's look at bigger things. But they made a change to the convolution, which is they said, let's change it from the convolution that we taught you to something which is called depth-wise convolution, which means you only do convolutions for each, if you think about it, each channel on its own. You don't combine information in this convolution across channels. So you look at neighboring pixels, namely 7 by 7, so you have the neighbor, and then you have the neighbor out, and then the neighbor out past that. Let's look at all of that together, do a filter on all of that, but channel by channel. Then they do a layer norm. So they get rid of batch norm. They just use layer norm. That creates much simplicity by using layer norm. And then they say, okay, if you look at this problem, we're kind of, each batch norm should think of as like a speed bump, right? Do we need this many speed bumps for the gradient? We can kind of maybe just have the one. Okay, so they just put the layer norm there. And they got rid of the norms other places. Then they said, let's now do linear combinations that are across the channels. So here there's a mild nonlinearity here only, which is the layer norm, right? But not a serious nonlinearity. So it's kind of like, okay, so you think of this, the combination of this is, it's like doing it's kind of spiritually like doing a 7 by 7, 384 convolution, except it's much fewer parameters and much less computation to do it this way. Right? You're still getting kind of something that's sort of a linear combination of things in 7 by 7, except it does it in 2 steps. 7 by 7 channel-wise, and then, make out 384 different linear combinations of those, combining across channels. Then they put a nonlinearity, and the nonlinearity is basically a ReLU, except it's called a Gaussian ReLU, okay, GeLU. And then they say, okay, one more, let's stick in a 1 by 1 linear layer at the end of that. And that's the block. Okay, so you can think of it, there's a real sense in which this thing is like a simpler version of this. It's kind of, in a way, a distillation of what's going on here, to be more kind of getting to the bare what you actually want. And the other thing that's happening is you're using a larger size convolution. Okay, so comment here is, this residual connections, you definitely keep using them. You start using this depth-wise convolution. I'll show you a slide of just to make sure you understand it, but it should be. Okay, so this is, any questions on this? I'll explain in a moment what this thing is so you can understand what it is, just because it's something you haven't seen before. But any questions on the basic structure here? I'll explain both the depth-wise convolution in case you don't understand that, so don't ask about that. And I'll explain this, but just the basic idea of what this block is doing. Yeah?
What's the saving in terms of parameters?
So they aren't actually going for an overall parameter saving. You can multiply it out and see what happens. What they're basically going for is this only looks 3 by 3. So this allows them to look at a larger neighborhood in one block. But if you just did that, if you just made this a 7 by 7, this would be very big. So the overall effect is to allow it to look bigger without having a significant increase in the parameter count.
Is there any significance to the difference in dimension for the input?
Good question. The question is there a significance for the difference in dimension? Yeah, it's keeping less stuff around. Again, it's to make the computations more tractable. Right? If you carry, if you look at this, you can count the total activation sizes that are needed everywhere. Right? So this, if you had made that as 256, it would be a lot bigger of stuff to carry around. Okay, so if you look at this GeLU thing is interesting. So I'll just first show you the picture of it. I just took the picture from Wikipedia, right? Here's the ReLU, here's the GeLU. Okay? So the interesting thing is that there's a formula for it. We use the Gaussian CDF. So it's x times the input x times the Gaussian CDF of x. So when x gets very large, the Gaussian CDF is approaching 1, because most of the probability of a Gaussian is on that side. And so it looks like a ReLU out there. But it's different kind of around here. So the inspiration for the Gaussian ReLU, the GeLU, is that you're kind of asking, hey, in a ReLU you have this max, 0x, right? So what's so special about 0? Like, why did I pick 0? The max of 0 and something. Why can't I let the 0 be any small number? You see like how you might naturally think that? It's like, what's so special about 0? And so what you can do is you can say, let me do, I'll pass something through only if it's bigger than a Gaussian n. And I'll just return 0 otherwise. Okay? It's not quite max of Gaussian and 0, but it's kind of like gating by a random thing and being 0 otherwise. So if you do this function, which is, if x greater than n, where n is a random Gaussian, return x, otherwise return 0. and you take its expected value, you'll get this. Okay, so it's kind of how someone could have thought of it. When you first look at it, it looks totally bizarre. Like, why would you do this, right? It's interesting because it has, the gradients are, they're softer here, right? So you actually have some gradients on this side that are still pointing kind of in the same way. But then on this side, it says, nah, point the other way. Right? So instead of, and around here, it's of course basically dead. So it has interesting little behavior. It was found to work a little tiny bit better in certain problems, so people use it. It's not, we don't fully understand why this works better in some problems, but so it seems to be empirically true. Although in the Convex paper, they said the actual gain they got from using this as opposed to ReLU was quite small. But it's a good excuse to talk about it, because it's used all the time in language models, too. Any questions on this activation function? Yeah?
So computational speed, is it slower or faster?
It's a great question. In terms of computational speed, is this slower or faster than ReLU? It's hard to beat a ReLU in terms of computational speed. It's like extremely simple. But you can there's tricks and optimizations that things do to make this not be that much slower. You approximate it, basically. You then approximate this guy. Like, no one's going to go through and grind out, the integrals for defining the Gaussian CDF every time. Like, you don't do that. Right? You're a little bit smarter. Yeah.
Does the non-convexity of the gradient ever cause problems?
That's a good question. So the traditionalist perspective, looking at optimization problems, would say, okay, this is like really weird because it has this non-convex behavior, and it has the gradient doing a kind of weird thing on the other side, and so we should be kind of a little bit afraid of what this is. In the deep learning context, the general feeling is that, look, your outputs are seriously non-convex functions of your parameters anyway, even if you're using ReLU, just because of the depth and how everything's combining. So, in for a penny, in for a pound type, it doesn't really matter at this point. Like, the fact that this is, this particular little element is non-convex, I'm not really that worried about it. That's kind of practitioner's point of view on it. Theoretically, understanding, I think people are working on it, saying, okay, when do these still work, and treat them as perturbations of ReLUs, and can you kind of generalize certain provable results that we know for ReLUs? But I think that wasn't the motivation behind people doing this. People tried it seemed to work. It was more that, hey, what's so special about... So if you can think about this, actually, that should actually remind you of the spirit of what's going on in dropout. Okay? What dropout does is, remember, what dropout you're doing is you're adding this regularizing force to your network by basically adding random perturbations to what your network is doing at every given time. Right? It's a multiplicative perturbation. Like, it changes things. In dropout, you take things in and out. So the analysis of dropout that people did to show what its regularizing effect is, I mean, we made you do in the homework versions that were elementary and simple in the context of linear, which I think we believe kind of gave you the spirit of what's happening and are more distilled than the initial papers. But some of the analysis in the initial papers, and you see even in the analysis that you did, all that really mattered was the fact that you're multiplying by something. The fact that you're multiplying by Bernoulli didn't matter in the analysis that you guys did in the homework, right? I mean, it did in the first one you did in the notebook, where it was very clear. That was meant to be the most easy to understand what's going on, that you're solving a mixture of problems at once. But the one you did analytically, only the multiplications mattered, right? So from that perspective, people started thinking about, okay, maybe we should think about other ways that we can randomly perturb networks and then have the expected value of things, the same way as dropout, run during inference time. You guys see the connection of ideas? How the ideas are like flowing from one to the other? Once you start thinking of that, it becomes natural to say, hey, where do I have something that I can randomly perturb that will keep similar qualitative behavior but be different. So this max 0x is definitely one of them. But once you do that, you already start thinking about, for inference, I'm going to use the expectation, and then it's a natural experiment to run, is that what if I just ran that all the time? You see? Once you start doing it, and you say, okay, that worked pretty well. Okay, forget all of the dropout-like thing where I do max nx and other if, and then train that way, and then do the expectation, just use this. So this is often how ideas develop, right? You come up with something you want to try, inspired by reason A, right? Then you follow it through to its kind of natural engineering consequences, and then you be disciplined about it and say, okay, now just looking at this, let me look at it again and prune it back to run the minimal test of what actually is helping or not helping. And then by this point, you might end up with something that is no longer connected to the original reasons at all, but is still helpful. Okay, so it's like a little aside on stories of how experimentation is done in deep learning. Moral is, it's good to do things it's good to have principled reasons to come up with good guesses of what to do. Once you have good guesses, though, you have to try them out. And then you have to understand them on their own terms and not be so attached to your original principal reason for maybe doing something. Anyway, so that's the GELU. Depth-wise convolution, it's just, here's a picture, it's a nice picture. It just has, you just do convolutions layer by layer, and you put the results together. Yeah, another little picture. Okay, so do you do it separately? Does everyone understand depth-wise convolution? It's not that tricky a concept. It's very natural. The biggest problem for many students actually is they first think about only depth-wise convolution as being interesting, and it's the other convolution that's trickier where you multiply across all the different channels. But it's simple. So anyway, the result of this actually was that doing all these things, right, you actually got performance improvements, significant performance improvements. So these are like ResNet 2015, like how good is the top one accuracy on ImageNet 1K, and the convex architecture at the same size, right, same size model is significantly better in how well it does. So is the only thing that convex does is use, relative to ResNet 2015, is to just use a different architecture? The answer is no. There's other things. And in fact, it's an ongoing, interesting question in the field of how much does the actual architecture matter compared to everything else that's also in play for how your performance is. So, they use a particular learning schedule, which people have used, called the cosine learning schedule. You can read about it. Again, this is found by practice of how do you have the learning schedule kind of go be high and then drop in a particular way. And then also other things you can do. They use Adam, in particular the variant of Adam, which is Adam W, which basically says let's have the weight decay separate. Like don't try to mix the weight decay into the gradient. So don't compute the derivative of something with the regularizing term. Have the weight decay out separately. Because you don't want to have the adaptation mucking around with the weight decay. Use the more aggressive data augmentations that we talked about instead of the classical ones that ResNet would use. And you put all that stuff together and you get this higher accuracy. So here, I did want to talk about a couple of these regularizations. Again, a little brief comment before we move on and talk about other things. So what are some of these other regularizations that you use? I mentioned it before, but I just want to make sure it's complete. You guys get a chance to ask questions about it. So something called stochastic depth regularization. Okay, so you know what that is? This is basically dropout for ResNet blocks. It's exactly what it sounds like. The entire ResNet block, the F, just randomly gets dropped out. Okay, so instead of multiplying the output of an individual activation by Bernoulli 0, 1, you kind of gate out the entire block randomly, and you put it back in. So what it means is, by doing stochastic depth regularization, it means that the effective depth of the network is random. And which of the, quote, layers of this thing are actually present is different. So this is the same thing as same kind of feeling as dropout. It encourages the, so remember, what does dropout do? Kind of at an intuitive level, we talked about it. You saw more mathematically what it did. But at an intuitive level, what dropout does is it encourages you to share the work across the different things instead of having them very specialized to do one thing. That same thing applies here, except it's for the entire layer. So this is used to improve performance. So improve generalization performance. Any questions on this? This is quite simple of an idea. Okay, good. It's because trying to do dropout individually on the channels is like weird. This is a more natural kind of dropout for convolutional type things, for ResNet type things. So the other one I want to talk about is called label smoothing. Okay, so this is dead. Is this one? No. I mentioned it before, but I want to make sure I can write it on the board. So label smoothing is when what you do is, so if you think instead of say class 2 being 1 hot encoded, to that, smooth encoding to like some small number 1 minus something small number, small number, small number. So just adjust this k and make this so that things add up to 1. Okay? Right? Like this is what this basically says is that for supervision of cross entropy loss, you, instead of saying that, if you view cross entropy loss as being a loss on probabilities, that says you want to think about the scores coming out, softmaxed as being probabilities. Does everyone understand this, what I'm talking about? So the output of a linear layer goes through a softmax, turns into things that look like probabilities, right? Because the normalization the softmax does. And instead of saying, what cross-entropy loss says is, I would like those outputs, traditional cross-entropy loss used with traditional one-hot encoded labels, says, I would like you to say 100% for the training class label and 0 for the others. The only way you could do that is actually to emit an infinite score for the true class, for the true label class, which is very hard to do. So it basically keeps striving in that direction. Instead of doing that, just say, yeah, I'm pretty sure you're a label 2, but it could have been anything else. Okay, so this is called label smoothing. Label smoothing also turns out to often help. And why label smoothing helps is not fully understood. there's many explanations. One explanation that is given for why label smoothing helps is that you might have errors in your training data. And so this is, at least limits the damage from that error. That's like one kind of intuitive explanation. But there's a more optimization-oriented explanation as well, which kind of focuses on that thing about it's impossible for the optimization to reach this in a finite set of parameters. Like reaching this requires you to move towards infinity, to go to larger and larger parameters. But it is possible to hit this with finite parameters. And so this kind of just allows that to happen. Yeah.
Totally off base, but analogy would be like soft margin SVM.
Actually, it's a good question, and the connection to margin and SVM is interesting. So in soft margin SVM, it's a great connection, actually. So if you think about soft margin SVM says that, okay, I'm actually going to tolerate some points violating the constraints. So some points, it's okay if they're not on the right side of the classification boundary with sufficient margin. I'm not going to bend the entire classifier to do that. So in that sense, soft margin SVM is, you can think of as being actually a regularization on a hard margin SVM. It turns out that if you don't think about data augmentations in particular, that for these kind of deep networks and the training data we use, the number of parameters you have is almost always larger than the number of data points that you have for these problems, which means that labels right or wrong, you can separate all of them. So it's kind of, in that sense, it doesn't, and you don't have to work particularly hard to do it either. That's the more surprising thing. So you could think of it as, okay, even that, the whole point of soft margin SVM is that, the SVM might go into a very tortured state to kind of try to fit all those labels, and soft margin says don't do that. In that sense, there is a spirit connection, but it's not exact. Okay, and the reason is that here, it doesn't have to torture itself really to separate everything out. But there is a sense of it, is that, okay, just certain data points, just view them as being satisfied, and like stop sending gradients on for that. And then people actually think about label smoothing with a smoothing schedule, right? Where they'll say, early on, let's smooth our labels a bunch, and then later on we might, move to something closer to this, which is in spirit related to what you're saying with the soft margin SVM. It says, when you're training, if you can get some points satisfied, just let them be satisfied and stop contributing significant gradients to moving things around, so you can allow the gradients from the points that are not as well satisfied to kind of have more of an overall effect. I mean, this is still, it's like shades, right, of difference because of how the gradients actually look like through softmaxes. But this is something you should be aware of, is label smoothing as another regularizer that is used. Okay, so yeah, that's what I wanted to say about this. Like, the actual real-life use of convnets for classification problems, there's a whole other level of little intricate tricks and things that tips that people use. We should read papers. Read the papers, see what they're using, read the code. They're often deploying these interesting other things. There's a group of people who are very much interested in publishing what they call training recipes, which are kind of combinations of things to use that seem to work well in training things both fast and effectively. Those are worth looking at and reading the same way that if you're an experienced cook, you want to look online for recipes, right? It's like, oh, that's interesting. Let me try that, And so I encourage you to approach it with the same kind of eye. Something cool to try, see what happens. Not everything is fully understood. There's a lot of art in practice in doing this. Okay, so Any questions on these things, on the basic understanding of ConvNets for supervised classification problems? Okay, good. So before I start into graph neural nets, I did want to acknowledge that not every image problem, not every vision problem is, here's a picture, please tell me a label. And you can see, so we've talked about it in terms of multi-class classification, but you can think of the same architectures you could use for regression problems. Right? Here's an image, give me, here's a picture of a room and what people are wearing, estimate the temperature of that room. Right? Sure. Regression problem, you know how you could train it. Right? You just change the last layer and loss, it's all good, right? But that's not all the kinds of problems that one has in vision. So I wanted to kind of switch to talking about something different. Hold on, just some more computer vision problems. So again, this is adapted from Sergey. I'm just going to do a briefer version of it because I think it's going to give you the idea. So you have problems like this that you know how to do. Okay, but there are other problems that are interesting in real life. So here's a problem kind of from, how do you want your self-driving car to look? Do you want your self-driving car to look at the scene through its cameras and say, person, cat, right? Dog, tree? No, right? You want it to have a spatial awareness. So you would like something that's closer to this. Right? You see a scene and you say, okay, on this scene, there's certain categories of objects in certain places. And you're worried about the fact that there's a person type object, here. Categorizing is very different for the person type object to be here than to be over here. Do you see that? Like how, from a practical point of view of using deep learning for a practical problem, just simply labeling a single label might not be the thing of interest. So there becomes a question of like, how do you adjust what you know to solve this other problem? Okay. So first, let me just set up the problem. This problem is you're given a scene. Still, this is called the semantic segmentation problem. You're given a scene, and you have a bunch of categories of different kinds of objects. And you want to just label the scene with every pixel marked by what category of object does it contain. Is the problem clear? Anyone have a question on the problem? So you all see how it's a very natural problem. It's, in a way, you can think of simply classifying a given picture with one label is kind of like warm-up. Like it's not even a real problem, right? Where this is a real problem. Okay? So it's an interesting thing, right? Which is that if you think about the self-driving car example, sometimes you don't worry about, like here, for example, in this picture, sometimes people ask, there's many cows here, but you just have one big blob labeled cow, right? All blue. So in some problems, you care about actually classifying different objects differently as being, okay, this is one person, here's another person, here's another person. But sometimes you don't. So again, in the self-driving car case, you might not care. You just don't want to hit you don't want to hit one person, you don't want to hit two people, it's kind of, it doesn't matter whether it's one or two. And sometimes you do care, and that's a separate problem. So if you wanted to do this, you could do it, like if I asked you to solve this problem, right, and you just used what you know, you could solve it this way. Okay, so what does this picture represent? What this picture represents is, normally, so you know how to make a classifier, right? And now you want to make a per pixel classifier. So you could just replicate everything for every pixel. Do you see that? So you could do it the completely dumb way, which is to simply have a separate neural net for every pixel, which would be insane, okay? Or you could say that actually just don't ever reduce the size. Right? Just keep doing convolutions, and then at the end, you're just going to have a bunch of 1x1s to do classification. Just put a 1x1 for every pixel, and then you'll get a bunch of scores for every pixel, and then take the argmax, and you'll get this. Do you see how this is an approach? Like you would just kind of what are the naive approaches you do? Naive approach 1 is have a separate network for every pixel. That's crazy, right? Now second, okay, just keep the convolutions the same, but keep them big, and then just do a 1x1 at the end. You could try this. So this is painful for two reasons. One is there is a significant amount of computation, but you also have the problem that maybe this won't actually learn what you want it to learn. Right? Like maybe if you just train this end to end on this problem, it might not learn what you want to learn. So why would that be? It could be that, well, the original network you had this, by having the size get smaller, by having those pooling layers and things like that, you were actually inducing an inductive bias for creating hierarchical structures. By eliminating that, you no longer are doing that. So maybe now you won't learn the right thing. If you just stick a bunch of convolutional layers one after the other, and then stick a one by one convolutions at the end to do the classification. Do you see that? Like there's an issue. You've changed the architecture, and you've changed inductive bias. So you could also say, well, no, let me just train it on recognizing images by themselves for a single label, the thing that's in the center, and then just kind of translate that architecture over here. Like learn with bottlenecks and just translate it over. But that still would have the problem in that you would have potentially, you're not actually training on this problem. You're training on a different problem, and then it could be that certain objects are really attractive, and so you end up having these edges like blur in, because the receptive field here still sees the other object a little bit off to the side, and it's like, yeah, that. Okay, but you want it to be for this pixel. So there's a question of how do you do this and make it work. So one approach is to say this is called the fully convolutional approach to solving these problems. And remember, there's an entire class, 280, on computer vision. The only learning goal here is to teach you a few little components, but also to kind of hopefully help you think about how does one actually adapt ideas? Like how do you reason to move forward in these cases? So you think, I want to have things where I get the inductive bias that comes from having stuff get, from high res to low res, this fine to coarse. So I build that in. But then what I got to do is I have to still build back out to get something big, right? Because the final thing I need to do is to be the same size as the original image with labels for every single pixel. So maybe I can do it this way. Okay? So if you think about it, what's happening here is that in Spirit, as the slide describes, you have you want to learn some kind of feature building that helps you distill out what's essential to understand what's going on. You want to have some low-res representation with many more channels that is capturing kind of contextual information from across the entire image. But then you need to do some kind of upsampling at the end, where you can interpolate these low-res things into high-res predictions. And that's the challenge. Everything we've talked about so far, we've talked a lot about how to go downsampling, but not how to do upsampling. So the question becomes, how do you do upsampling? Yeah? Yeah, it's a great question. We'll talk about, we'll review autoencoders and stuff later. But might as well talk about it now, right? So if you remember, in your machine learning class, you learned about dimensionality reduction techniques like PCA, where you said that, hey, you have a high dimensional space of inputs, but you know what? Let's just look at the directions of greatest variation. Those give us a subspace in which we think the interesting action is, and instead of running a learning algorithm on the original high dimensional space, we run it on the low dimensional space, where we expect to have, a more reasonable connection between the number of samples we have and the size of our data. Classical ML, right? Now, you can also, because of the Eckert-Young theorem, you can think about PCA as actually solving a problem of find the best low-rank approximation for the input data. And that can be viewed as an end-to-end problem of take the input and reconstruct exactly the input at the output, except force yourself to go through a bottleneck where you have a lower dimensional space. Okay? That's like it's a reinterpretation of what PCA is doing, because you understand the Eckert-Young theorem says that the dominant singular vectors give you the subspace which minimizes the loss of Frobenius norm in the matrix. If you don't know what I mean, that's fine. Just for those who do, I'm telling you. So you can get this connection. We'll talk more about this in detail, but I want to answer your question. So now, once you understand that view of classical dimensionality reduction, you can say, let me simply use a neural net so I can do nonlinear dimensionality reduction by training end-to-end for this self-reconstruction problem. That's called autoencoders. Again, we'll talk about it later in more detail. That also has the similar structure, where you start big, get to something small, and then get back to something big, where the goal is, without labels, to generate good intermediate representations that capture the directions that seem to matter the most. Okay? This problem is different in that while it maintains the same structure, it's actually fully supervised end-to-end because I have these semantic segmentations already labeled for me on a per pixel level. So I'm not trying to reconstruct the same thing. I'm reconstructing something different. So if you want to, and if you're aware, you might think of this as like a CCA style, right? Where I have canonical correlation analysis, where I have actually different vectors, and I want to find the kind of appropriate low-dimensional alignment between these different things. But yeah, I mean, it has architectural similarities, but it's different in that it's not an autoencoder. You're not trying to reconstruct the same thing on the output. It's something different. But like, it does bring up this issue of how do you go back out? How do you go from something small to something big? And to understand this, we have to understand there's two operations that we did in a CondNet that could make something smaller, right? Those were, we could do a strided convolution where we simply just skip not one, but two things at once, and then we get an image that's half the size out. Remember? So strided convolution results in a reduction in size. The other thing was like pooling, like max pooling. So we have two operations that we know we're doing over here that will help us make things small. So we need to understand, like, naturally, is what is their counterpart that makes things get big? Is that clear? Like, just like, great. You kind of set up, what's important to understand is that you set off looking at the problem. You say, I need an object. I need ways of doing this. And then you figure out, how can I do this? So in this particular setting, what you do is actually, you literally take the signal processing idea that would do it classically, and you just replicate it for your setting. Upsampling and downsampling are classical SP operations that you learn for undergraduates, learn in a class like 120. And you say, OK, I need the counterpart of that. And then you just figure out, what there should I make learnable? And the general rule is, what do you make learnable is filter weights. Okay, so it turns out to be essentially identical operations. So again, for people who know, SP upsampling. Okay, so in signal processing, you just have a discrete time signal where you have values here, 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 and here, you know, kind of spread out like this. This is, I should like throw them away. Right? You have values here, 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 and here. And you want to reconstruct values here, 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 and here, kind of in between values. What do? What you do is a convolution. You say, okay, I will take a filter response. For example, if I want to do, you know, like a piecewise constant thing, I'll say, okay, instead of this value, I will replace it with a box, and I'll put another box at a different height centered on this value. And I'll have another box centered at a different height for this value, whatever the height should be, a simple convolution, and I'll add them up. Right? So this plus this becomes this, then this, and then this, and so on. Okay? Like just classical signal processing reconstruction. How do you interpolate things? So it's the same thing. It's a convolution operation because it's a filtering operation. So let's just realize that exact thing. So the thing is called a, whenever you do it in the context of deep learning, you call it a transpose convolution. So here's a basic review. Here's a normal convolution, just nicely animated. We're going to have a stride. Okay, so we just move around like this. Is that clear? Basic convolution, so that's how things get smaller. Transpose convolution, so here I have a stride of 2. So what I want to do is I want to reverse it. So I want a stride of a half. So how do I do a stride of a half? Okay. So first is understand what's going to happen when I do a stride of a half. I need to go from a 2 by 2 to a 5 by 5. Okay, because I want to reverse this move from something big to something small. I need to go from something small to something big. There, what I did was I took an average of a bunch of things, right? Weighted average of a bunch of things to give me one value. Here I'm going to take one value and put a filter down and just copy it over. Okay? So take that value, take the filter. Here was a square, a box, any shape, learnable shape, and just copy those into here. Then follow the stride and move over. Okay? So stride of 1/2 means move 2 over here. They're used to move stride of 2 and move 2 on that side. Stride of half means move 2 on this side. So you move 2 over here, and then again you have a 3 by 3. I put down a 3 by 3 set of stuff. Of course, they're going to overlap. That's the point, right? And when they overlap, average. In traditional SP, you add, but averaging is the same. Okay? Any questions on how this works? Yeah.
You ever get a stripe artifact from the fact that, like, for some squares, you get, you know, if they're overlapped too, but
Yeah, great question. So the question is, you know that in traditional SP, if you do very simple boxes and use those to interpolate, you will see visual artifacts from these boundaries of what's happening. So like the low-res thing will still, your upsampling will still have this kind of artifacts in it. Everyone, like, you know, if you just take an image and make it bigger by like copying over and doing this, you'll get these like stripes and bars. What's the solution in traditional SP? You apply a filter afterwards to smooth those out. The same thing is here. So always after you do a transpose convolution, you will then have a filtering operation to remove artifacts. Great question. So again, the idea here is nothing new. Whenever you can borrow something and simply adapt it by saying, what did I do in another setting? Let me do the same thing, except where I had from physics parameters, I'll make those parameters learnable. That's the general way to move. Yeah.
Are you learning the like smoothing filter afterwards?
Yeah, you're learning everything, right? So in a convolution, you learn the entire convolutional filter. So here, you learn this entire filter too, right? And then if you're going to stick another smoothing filter afterwards, you learn that too. So great. Started convolutions, you know how to undo them, right? What about pooling? Okay, how do you unpool? So unpooling is basically, if you think about, so average pooling, you can imagine as unpooling it the natural way, to simply repeat everything. But for max pooling is a more interesting one. What you can do is you can remember which element was the max. Because if you think about kind of downsampling something and then bringing it back up again, you're allowed to remember. Because you built the architecture, right? You don't have to forget. So if you remember that originally you started off with something like this. Here's like a box. And you have the 5 was the max in this block, right? And then the 6 was the max in this block. The 7 was the max in this block. And the 8 was the max in this block, right? So then you went from this entire block down to this. Then you have a bunch of network stuff happening. And now you have this small thing. You need to unpool it. Remember, you're trying to undo everything you did. So wherever you had convolutions, you replace the transpose convolution. Wherever you had pooling, you do unpooling. So with the unpooling, I have this 1, 2, 3, 4, and I need to get a 4x4 output. So what you can do is you can remember which element was the max and stick it in the same place. You see how it's exactly the same flavor as pooling, except just reversed. And look what happens, though. What happens, though, afterwards is you get something that has zeros in a bunch of places, which is exactly how, if you think about it in traditional SP, when you're doing upsampling, there's this intermediate step where you have zeros. You get the rate right, but you have zeros in all the positions that you don't know. And then you use a filter afterwards to get those zeros to fill in properly. Same thing is true here. Remember, every time you have a pool in a convnet, it always was preceded by some conv thing, right? So now you're going to have an unpool followed by a filter. So again, it plays nice. So by doing this, you can kind of just create like a mirror on the other side of you got some way of getting down, get back up, and learn filters to do that. Okay? Any questions on this basic philosophy of how you kind of deal with things that are not simple classification? Yeah. Yeah, for average pools, you can fill in the same number, right? Or if you want, you can fill in, yeah, you can fill in the same number. It's like a learn thing afterwards, right? So like it'll deal with it. Or you could just fill in a quarter. Like you could, for average pooling, you could put a quarter, 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 quarter. Or you could put in 1, 1, 1, 1, 1. It doesn't matter. The next layer will, whatever you learn, the filter coefficients of the next layer will take care of that scaling for you. Okay, so this works reasonably well, but it misses something. And what it misses is that when we think about natural images or things in the world as having a find a course structure, we think of the course as defining the essential things that might be happening, and the find is like details. But the details can matter. And so there's details that you're throwing away as you move from find to course that might still be relevant to reconstruct at fine scale. Do you see this? There's like an issue here. So for example, the typical, so this is, if you ever study something called Kolmogorov complexity, there's this kind of decomposition that people think of as, okay, you have the idea of a cat. Here's a cat. Then you have the cat and the cat's pose, right? And then you have like levels of detail, right? Like, okay, now where is the actual fur on that cat? Each of these are different levels of detail. But depending on what you want to do at the reconstruction, different aspects of those detail might matter. So if their final reconstruction is a pretty zoomed in or very high res image of the cat, and you want to actually label the fur, like individual hairs, right? That's different than if you just want to label the cat and the cat's shape. And it's different than simply saying cat somewhere in the image. Like the details of the pose matter they don't matter for the cat, but they matter for labeling the individual pixels of the final image as being cat or not cat. Do you see that? Like small variations. So there's a challenge that information can be thrown away, legitimately thrown away as you're moving down, but is actually needed to get the fine alignments right over here. So how do you deal with this? So for this, there is a classic trick that's called the UNet architecture that's used to do this. And what it says is that this is the picture used to understand UNets. So you think about the finest thing is on top, and coarser things are down below. So you think about the evolution of your network as being, okay, I go from things that are fine, and then I get things that are coarser, and I get things that are coarser, and I get things that are coarser, and then coarser, right? And now I want to go back up. So one way of going back up is simply the things we described, right? But remember, every time you did one of those flipped steps, right, the transpose convolution or the unpooling, you always had a filter afterwards, right? You always had a filter afterwards. So the trick in the UNet is to say, hey, I'm going to have a filter afterwards. So why don't I simply give that filter also access to information at that level of fine coarseness that was in the previous thing. So I copy over everything that I had here, over here, and I give that filter access to both sets of information. The appropriately distilled and upsampled information, and the raw information at the end of that last level that still has fine structure in it. Okay? Do you understand the idea here? So the key thing here is this picture here. So it says you're doing upsampling. Right? Some learned transpose convolution, unpooling something. And you get a bunch of stuff. You're going to have to filter it. Learn filter afterwards for smoothing it out. You have to do this. So instead of just having this, have concatenate, quote, raw info from this level before downsampling. Right? Concatenate, by which I mean literally add those as channels. So now this filter has more information to work with and can use both sets of information to do what it needs to do. So this is the UNet approach. And the UNet architecture basically was the go-to standard way of doing this style of problem. It's used not just in the context of semantic segmentation. It was also very important for generative models like GANs and so on. So it's like a standard trick. So when you want to maintain information at multiple levels of fineness and coarseness, and you want to learn something that way. So what this does is basically it creates So you train this way. You train end to end. Something like this. It's trained end to end. So gradients are, you're hoping, are going to force the right information to be distilled here, and the gradient that's going to flow back this way is going to make this course level not lose too much, not give up too much. Also, because the information you need to do good reconstructions at this level will hopefully, the gradient here will tell you to keep that. So basically, it makes the gradient's force here makes the downsampling function by putting the right information that's distilled so it gets pushed down to the next level, and keeps other relevant information in the other position so it comes out. Whereas ordinarily, there's no force to do that in the gradient. Nothing in the architecture is making an inductive bias in that direction, but this hopefully is. So again, last comment. I'll talk about graph neural nets next time. This is was the go-to architecture. Today, it's still used in some places, but different transformer architectures are supplanting some of these things. But it's still important to know as a case study in how do you engineer things that are specific to your problem. Okay, I'll take questions now here because there's no class, and then I'll switch office hours over to the 258.